All right, we have this second order ODE for starting off. I was thinking, how the hell do I start this? I'm not done with exact differential equation. I don't have a real life example for it because all of these have some uses, some weird uses. I'm really proud of this ODE. But for the second order ODE, we always want to start with something like gravity. And a common example is a mass and spring. But a lot of people, I don't think, explain it well enough when they talk about mass and spring things because it really just makes no sense. It just confuses the hell out of me sometimes how they explained it. Um, so I'm gonna explain it in my way that I understand. So what I would say is no gravity and yes gravity does not really matter with the ODE, mainly due to this fact over here where they cancel out, where we can even imagine it with the massive spring. If you do have a massive spring somewhere here, I don't think we do. Ah, shucks. Pineapple. There's no. I don't think so. Anymore. So okay, there's no massive spring. Okay, so we're gonna use my phone with this ridiculous example. So imagine this is a spring, and we have no gravity. Then if we bump it, it'll be like this, right? It will just go. I hate this already. Um, this is a bad example. Okay, we'll use this again. All right, so we have if this was the attached to a massive spring, it will go up and down in a vacuum, right? Forever and ever. No friction, no dampening, no shenanigans. Dampening is just friction. It's not really anything different. It's air resistance too. It's also thermal released a little bit. Anyway, so technically speaking, it would be. This is why it is perfect with no gravity, obviously. But when you add gravity, you're adding additional force, but it will go to equilibrium. They just make a new equilibrium. So, in reality, the ODE does not change. The ODE is the same. And really, I should write that ODE down because it's not that hard to write down. Honestly speaking, that ODE without dampening, uh, ODE for um, no, what was it called again? I forget. Uh, no dampening. So is equal to basically we have this thing right, mg, and I believe is minus kx. So we actually get rid of the mg because in reality this is what happens. I'm gonna have to rewrite this again because I really want to show this off multiple times. So what would happen is that this would turn to this situation. Now notice that Ks is the mg. So what happens is basically no matter what, if it's gravity or no gravity, gravity doesn't really matter in the sense of this is the equation. And since k is always positive, when you write this ODE, you always want to move it to the this side to make it easier to get the auxiliary equation, which we'll talk about later. Maybe I don't know. Maybe tomorrow. I don't know. So we have a plus here. So we can always say that k has to be plus, and that makes sense because k is a spring constant. And a spring constant is a measure of the string's like toughness and other stuff, like when you're longer than everything. So it makes sense that k would be always above zero, or maybe even zero. Zero probably is a string. You can't get a negative string value. I mean, technically, you probably could if the spring is somehow uh, when you push, it pushes faster. So it's no longer a spring; it's like a projectile. Then it kind of makes sense, but even then, you're stretching the definition of a spring so much that it doesn't really make sense. Anyway, this is a definition of OD, which makes sense when you divide this over here. I think we'll talk. I put a lot more in physics, so I won't really talk too much because we do revisit in physics again. So over here we get this formula over here, which is omega, but omega squared. So the square root is omega. And there's a reason for that. It's all due to energy, which we'll talk about in physics mechanics. It's not really that hard, and I need to restructure that physics mechanics anyway, so we'll deal with that later. So this is true. So no dampening, and it's the same ODE for um, same ODE for no dampening gravity. So you can kind of see that these two, yes, gravity, no gravity, in just a spring. If there's another like system attached that has some kind of weird mass with a vertical mass and some kind of weird shenanigans that goes like this, like those masses that those springs that you arc it. There is things like that that I will not mention, and then there's also cases where the spring has mass and you have to figure out the moment of inertia and other stuff. Actually, you have to get the center of mass too because if their mass is no longer the ball. But generally speaking, the spring doesn't really matter with the mass because it's negligible compared to the mass of the ball. So what I'm saying is big mass compared to, assuming I should probably write that somewhere. Assume that a ball is much greater than a spring. A spring. If 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 uh if the spring is much massive than the tiny little thing over here, then all of the math goes wonky because if you're pulling on this, you're pulling on the. I mean, your center of mass is way off, and you're just gonna have a little bit of a painful time figuring all that out, which will be a coupled equation too. I don't want to do that. But is it possible to do it? Yes, it is very possible to do it. No, I'm not doing that. I'm not even gonna do that for now. It is a coupled equation, probably multiple springs attached. Yeah, I kind of know how to do that. You need multiple boundary condition, initial conditions on both velocity over here, in the middle over here. Um, but we're talking about basics right now. I will add that later when we talk about coupled and forces because I do like that. I do want to do boundary condition with multiple boundary initial conditions that are necessary. But that's more of physics actually. Maybe I'll do it in the physics mechanics section. Anyway, no dampening and then we have dampening. That's pretty much it. And all of this is different ways for that to appear, which I'm gonna clean up. It looks shitty right now. It looks pretty shitty actually. And there's also forcing, which is how we have the initial condition. Right now I have an initial condition of VO. Now that's one way to do it. But there's another way called forcing, where there's like a force over here that you have to initially cause, and that initial cause is translated into the ODE. We'll see about that later. Anyway, you can kind of see how adding dampening would be this. There's a different type of dampening. There's critical and another type of dampening. I believe I talk about it. There's critical dampening and I forget the other two. Here it is. I'm gonna clean this up. Under dampening and other stuff. I will clean that shit up. This looks awful. It looks kind of what's the word? A joke. Yeah. So first we'll start with this one. Yeah. Yeah. I never liked how other how I was taught this section. I think this does a good example of what it looks should like. I mean, in my opinion, this looks pretty good. In my opinion, on how it should look like. Um, yeah, ODEs, lovely. Starting ODEs, making ODEs